I'm Henry Gilliland, the motion specialist with ES&E. Tuning servo motors can be nerve-wracking and often seems extremely complicated and difficult. However, I'm going to show you how simple tuning can be when you're using Rockwell Automation's integrated CIP Motion over Ethernet IP. In the previous video, how to use auto-tune for servos, we used the auto-tune feature in Rockwell's Studio 5000 Logix Designer to maximize the performance of our servo system. In this video, we'll use the manual tuning tool in Logix Designer to fine-tune our axis and discuss the interplay between performance and component lifespan. We will also examine what happens when a servo system is over-tuned and pushed to the very edge of its capability. This video builds on the previous two in this series, so if you have not had a chance to see those, simply click in the link in the description below. Let's get started. The first thing we'll need to do is adjust the scaling of the position error. This will allow us to get a magnified look at the following error as the axis moves. To edit the scaling of a pin, just right-click on the trend and select Chart Properties. Then, in the Pins tab, adjust the scaling under the min and max. For a closer look at the error, we'll set the window to plus or minus 0.001 millimeters. This will allow us to see minute changes in the position error over time. The next step is to open up the manual tuning window. Right-click on the axis and select Manual Tuning. The manual tuning window can also be accessed from the axis properties. In the manual tuning window, there is a selection of motion direct commands that can be used to move the axis manually. These manual instructions are very useful for testing live adjustments in axis tuning. Since the axis is already running, we'll start with a simple index move. Select MAM. We'll do an absolute move to 140 millimeters at 80 millimeters per second. We want to reduce the following error as much as possible. The purple position error trend is showing that the following error is currently outside of the scaled window. We'll now make an effort to reduce the error until it's inside the window. We'll continue adjusting the tuning until the following error is as small as possible. Another quick index to review the motion. In the manual tuning window, there are many different adjustable parameters. However, for most applications that require manual tuning, the only parameter that should be adjusted is the system bandwidth. In general, the higher the system bandwidth is adjusted, the less following error there will be. Unlike the auto-tune feature, manual changes made to the axis tuning by adjusting the system bandwidth will take effect immediately. It's recommended to make small incremental adjustments to the value and then test the tuning. This process should be repeated until the desired results are achieved. As expected, the more system bandwidth is increased, the less following error can be observed. From 15 to 20 Hz, the average error decreases. From 20 to 25 Hz, the average error decreases. However, increasing the system bandwidth too much will reach a point of diminishing returns. Increasing from 25 to 30 Hz causes catastrophic destabilization. There is now severe and persistent resonance. This is a clear indication of a servo system that is over-tuned. The resonance that is visible on the trend will usually be accompanied by an audible hum or buzz from the motor. Increasing the system bandwidth further will only increase the destabilization and cause the resonance to get worse. The only solution is to decrease the tuning by lowering the system bandwidth. The resonance immediately goes away when we set the system bandwidth to 20 Hz. At this point, we have reached the best possible tuning of the axis, if the goal is to minimize error as much as possible. While the error looks significant with the current scaling, if we change the scaling back to plus or minus 0.1 millimeters, instead of the current scaling of plus or minus 1 micron, a quick adjustment of the chart properties will reveal an insignificant error. We'll see that in reality the error is virtually zero. In fact, it doesn't even register when the scaling is set to 0.1 millimeters. As noted, this is the best tuning if the goal is to reduce the following error as much as possible. However, for most applications, an error tolerance of under 1 micron is not required. In order to determine the tuning that works best for a particular application, it is important to understand what the true error tolerance of the application is. This way you can adjust the tuning to fit the application. This is a good practice because it will ensure that the axis is not over-tuned and working harder than the application requires. The looser an axis is tuned, the less stress it places on the electrical and mechanical components of the system. Let's say for this application, our tolerance window is plus or minus 0.1 millimeters. We will continue reducing the system bandwidth until the error is within 20% of the tolerance window. This will allow for some margin of error while still maintaining the required error tolerance window. When we reach a frequency of 2.5 Hertz, we are getting a little too close to the tolerance window for comfort. We'll increase the system bandwidth slightly to reduce the allowed error. Now we have reached the point of optimal tuning for this particular application. Every application is different. Some require more precision than others. The best practice is to tune to the requirements of the application. This means you have to know what the error tolerance of your application is. The error tolerance can be based on many different factors. It's important to know as much as possible about the mechanical and electrical limitations of your system before you begin tuning. However, the process we just walked through should help you get the best results for most position control applications. Thanks for watching, and please be sure to subscribe to ES&E TV for updates on all the products and services that we have to offer.